Morning again, and welcome to this session. Today we're supposed to do problems from chapter 28. The lab this afternoon, we have lab, but since I probably will just send you the instructions for it. There is the instructions already on Canvas in terms of the written instructions, but I'm going to probably pre-record the session, which I already did actually with another section of your class. So I'm going to post it there, and I will be available for you guys if you have any questions. So in other words, I will be live, but if in case you have any questions, please let me know. If not, you don't really have to attend that live session this afternoon, okay? If everything is clear. Because part of the lab this afternoon is it deals with the magnetic field and also the electric motors. And because the college ordered the materials for the electric motors, but they were never received before the actual midterm last week, so you were not able to receive the materials for the motors. So you cannot really build the motors, okay? So that part of the lab is basically scratched. So which means that now you only have a very small portion of the lab. I mean, it's really not a lot of activities, so it does not really amount to a lot of full lab basically activity like we normally do. So that's why it's kind of I'm going to basically post the instructions, the video instructions that is, on Canvas. And also I will be available at 5 o'clock this afternoon, just in case if you guys have any questions. If you don't have any questions and you find it as easy as I think you will, then you don't really have to attend it, and hopefully you will have no problems with it. Of course, like with anything else, if down the road you run into some difficulties and you have problems with it, please let me know so that we can work it out, okay? So that answers that one. So the other part also is today, like I said, we have several problems that I want to discuss with you in terms of how to solve them. So chapter 28 problem session. So let me share with you guys the screen and to discuss exactly what kind of problems we're going to be doing. Share. Okay. So the problems that I thought are worth doing are problems 28. Again, this is from chapter 28. So the problems are problem 38. Okay, it's very important that everybody does these problems. Don't watch me do them. You actually have to follow in writing in doing this problem. So whether you're watching it live or you're watching it recorded, you really have to pick up a piece of paper and start working on these problems, okay? And do them as I am doing them, and you make sure you do the calculations, because you will see that some of them probably I will not do the full calculations, but I'm hoping that you guys will do it, and so that you learn from them, because physics is not a spectator sport, and you will not learn from the lecturers a lot, honestly. The lectures are actually needed, but they're necessary, but they're not sufficient. Actually, you will need to practice in order to complete your learning, and the practice through doing problems, okay? So first problem is problem 38. You will see that problem 38 is identical to a similar problem that we did in the midterm, the last week midterm. And that problem actually had to do with the charges distributions, and we're supposed to calculate the flux of the electric field there in that problem. Today, problem 38 will actually deal with finding the circulation of the magnetic field. The words are different. In there, you were given charges. In here, you were given currents. In there, you were asked to find the flux of the electric field. In here, you were asked to find the circulation of the magnetic field. The method is identical. The answer, of course, is going to be different, because you're asked different stuff to find, and given different things, you're going to find different things. But the point in here is that the method used there is identical to this problem, okay? Problem 61 was an exam that actually, at least a version of it was in an exam that I administered actually last semester, okay? So it's worth knowing how to solve that problem. Problem 62 is actually similar to problem 64, and problem 64 was actually given also as an exam in the past too. So it's worth knowing how to do these problems too. okay? Again, we're not doing 64, we're just doing 62, and they're similar. Then problem 67. Problem 67, and again, is similar to a lot of problems we worked with in the past for charge distributions. Now we're given current densities, and the calculations are similar in a sense because they involve integrations and things like that. Although, again, in the previous, when we were doing charge distributions, we were doing summations over volume of the charges. So we're given a charge distribution in space, and we're supposed to add it up to find the actual charge enclosed, and we use Gauss's law there to find the flux of the electric field, and from there we find the electric field. Now we're given actually current densities, which means we're going to sum over an area. So the integrals, instead of being triple integrals, they become double integrals. And at the end of the day, neither in that time nor now we actually carry triple integrals or double integrals. We only at the end, by symmetry, only carry a single variable integral. So we didn't do it in the past when we were doing Gauss's law, where we carried actually triple integrals. I mean, the expression itself normally has a triple integrals, but because of the symmetry, we get rid of all of the other angles, and we were left just with a single variable to integrate. So that was basically the actual law itself looks a little bit awful, but when it comes to its implementation, it's a little bit easy. So that is a similar situation now. The actual summation of the current densities over an area, but again, by symmetry, for this problem 67, you will see that it's actually a single variable integration, okay? And it's a polynomial integration, the integral of x and the integral of x squared and the integral of x cubed. This simply should be the integral of x is x squared over 2, the integral of x squared is x cubed over 3, and the integral of x cubed is x to the power 4 over 4, and so on and so forth, the rules of the integration. Then after that, we're going to carry a little bit more complicated integration, and that one is problem 63. I'm not sure, honestly, if we're going to get time to do problem 63, but that's the problem that we want to do. And it's similar in a sense to problem 67. So this is similar in terms of the procedure, but the actual details are different because the current density is in here. It's actually a quadratic form in terms of the displacement. If you look at the problem, it has an r squared in it. And the other one is actually a combination of a fraction with respect to r, and also has an exponential. So this one is a little bit different, exponential dependency on distance, whereas this one is quadratic. I mean, this integral is like, if it's r, is going to be basically r squared over 2. If it's r, it's going to be r cubed over 3. And if it's r to the power n, it's going to be r to the power n plus 1 divided by n plus 1. Okay? Whereas in the exponential in here, it's going to simply be exponential. Of course, don't forget the coefficients and all of the stuff that I didn't write in here that needs to be dropped and added and things like that. So this is the difference between problem 67 and problem 63. And problem 49 is actually an interesting problem that I'm hoping to at least discuss the solution of it. So if we can get around to doing problem 63, I mean, if we run out of time, we're probably going to skip straight to problem 49 and basically say how that problem is going to be solved. I most likely will not be able to finish all the calculations, so I'm relying on you guys to finish the calculations. And if you have difficulty with it, please let me know. Do not struggle on your own, okay? Things that may be probably, you may be stuck on a small, tiny issue that has probably not, I mean, it may look to you it's a lot, but once you receive the info about it, it becomes so obvious to you that you're going to say, oh, of course it is. So you're going to move on. But if you're stuck in any place, do not basically struggle and give up. Please let me know so that we can clarify the issue that you're running into, and then so that you move and you solve the problem and you feel better about it. Okay. The key thing about all of these problems is you actually have to do them. Do not watch me do them, because if you watch me do them, you're not going to learn much. Okay. Again, lectures is a necessary condition, but not sufficient. And doing the actual problems is actually what is needed to really for the learning to happen. So again, I cannot really emphasize how important all of these things are. in terms of getting your hands basically handy with all of these things. Okay, problem 38. Problem 38, as I basically alluded in the intro, is similar to the problem that we had in an exam. So problem 38, again, the 6-step process. I know I gave you the piece of paper during the exam to how you think about solving the problems, and that is true for any kind of problem, okay? The 6-step process. So the first part of the process in here, so problem 38, is to basically read the problem and pull out of it what is given and what is asked. That's all, okay? So it's very important. You have to be careful and do that. If you don't, you may make assumptions that at the end will turn out to be wrong. So it says figure 2838. So it's probably worth drawing this figure in here. So let me draw this figure. This figure has current I1 that is into the picture, okay? And it has current I2 that is out of the picture. And it has current I3 that is also out of the picture. I mean, out of the screen for our case, okay? I1 is into the screen. And then it gives you paths. These are not areas. These are not closed surfaces. These are basically path. So the first one is path A in here. The second one is path B here. The third one is path C, which is here. And the fourth one is path D. Okay, and so that's the picture that they're referring to. In cross section, so basically shows in cross section several conductors. So these are not the actual wires. So this is the wire, for example. When you take it and you cut it from here, so this is a mathematical cut, not a real cut, and look at it this way, this is how it looks like. It looks like to you something like this, okay? Whereas in the first one, the current is actually coming from your end towards me, whereas in the second and the third one, the current is actually coming from this end to the camera to where you are in here. So that is basically what this picture is telling you in here. So there is a wire, I1, that has a current coming from where you are in here and coming to this way, okay? Whereas in the case of I2, there is another wire, not the same wire, that has a current coming toward that place in here, and the same thing with I3, okay? And they gave you the values. They said I1 is equal to 4 amps. There are 2 sig figs in here. It's worth remembering what the sig figs are. So that's when you're doing approximations, you know exactly which how many sig figs to retain in the answer. I2. So we're doing now the step that has to do with all of the things that were given in the problem, so that you're keeping track of where we are in terms of the process. Okay, and we're given I3. This too is given, by the way. The graph was given to us, and the picture, I should say, was given to us, plus this information. So I3 is equal to 2 amps. Technically, I should really write them with their sig figs, or write in here sig figs 2, so that I keep tab of exactly how many numbers I need to retain in my solution, okay? And the directions are shown. It is very critical to remember the directions. If I'm going to calculate any circulation, and that's where we are, the circulation is always counterclockwise. Now you're asking me, where did I get this one from? This is a common convention. So again, now I'm pulling stuff that I know from before, from the lecture. Okay, so this is the convention for the circulation. Also from the lecture now, from what I know is the current that is coming out of the screen will have a counterclockwise circulation. A current that is going into the screen by the right-hand rule will have actually a clockwise circulation. So that means that I1, again, this is Nothing to do with it. It's not stated in the problem explicitly, but it's telling you the direction is given. Therefore, I'm going to take I1 as negative current. Because it creates a magnetic field that circulates clockwise, and the circulation by definition is going counterclockwise. So I'm going to calculate then the circulation for I1. You better put a negative sign in front of it. The circulations for I2 and I3 is positive. See, the stuff that I'm putting in here has nothing to do, is not clearly stated in the problem, but I'm putting stuff in there that I know of, okay? What is the line integral of Bdl? 4 paths, that also is given. It tells you in here 4 paths A through D are shown, so I already took those. So if I'm going to calculate the circulation through path A, I'm going to go counterclockwise. Through path B, I'm going to go counterclockwise. Through path C, I'm going to go counterclockwise. And through path D, I'm going to go counterclockwise. Okay? So that is, in a nutshell, what we're saying in here. So now I have pulled all of the stuff that I have in addition to some of the things that I know. And they tell you to find the circulation of the magnetic field. So the circulation of the magnetic field now I'm going to pull something I know, is equal to, by Ampere's law, as mu naught times the sum of the enclosed currents. And this sum is an algebraic sum. So you're asking me, where did I get this relationship from? This is Ampere's law. Okay? So now I have put stuff that is given in the problem, and I added things that I know, and I'm ready to solve to solve and answer the questions. So the first one is on path A. Path A. So this circulation of Bdl now is along path A. This is equal to mu naught times the currents enclosed. And what is the current enclosed in path A? How much current is enclosed in this path that goes in or out of path A, inside this surface in here, inside this area in here, enclosed by this path?
Enclosed by the path, shouldn't it just be 0 since there's no I inside of it?
Current. There is no current. So the answer to this one is mu naught times 0, which is 0. And that is the answer to the question. I mean, I was a little bit, honestly, kind of, it was not really good that some of you started actually thinking about solving this integral. That's the whole point of Ampere's law. You don't do the hard stuff. Just look at the law and say, hey, the answer is 0. I don't care what B is. Because somebody might be tempted to think, okay, there is a current in here, so it might create a magnetic field in this point. And it is true, it will. And there is a current in here. And this current, this magnetic field is probably pointing this way. And this current in here will create a magnetic field that is going to be pointing this way. And this current in here will create a magnetic field that is probably circulating this way, probably circulating at a different angle. And this one is probably circulating at a different angle. And this one is, because you have to take the normal to this surface and find basically the way this one is circulating. Guess what? If you do it that way, you could. Nobody can prevent you from doing that. And if you are lucky enough, and if you are extremely good with integrations and with actually calculations of these complicated the complicated integrals, what do you think the answer is going to be if you actually do this calculation? When you sum up all, I'm sorry?
Oh, I was just going to say, wouldn't it still be 0?
Absolutely. Okay. You're going to get so many complicated vectors in 3D space, basically. In this case, probably it's going to be 2D because the wires are coming out of the screen. So all of the projections of the vectors B are going to be in the X and Y directions. But then at the end of the day, you're going to get a very complicated and nasty expression and waste a lot of time. And at the end, you're going to get 0. So instead, you don't do that. You just look at the picture and say, how much current is enclosed in here? Nothing. So hey, 0. Because you're going to sum through this integral through this path, which was not given to you at all. They didn't even tell you what that path looks like at all. So you have to really find the shape of that path and doing summations. Isn't this clever?
It is. It's a lot simpler than going through all the complicated things like you just said.
Okay, so I was kind of disappointed, honestly, when I saw some of you started to calculate those. In that case, it was actually surface integral for Gauss's law. This is Ampere's law. So path B now. I think you get the point now. Path B, I'm just doing the same thing in here without actually doing that. So it's mu naught times the current enclosed in path B. And the only one that is enclosed is I1. And I1, because of the way that if I do the calculation in here, if I'm actually trying to find this point in here, the magnetic field is going to be probably tangent to it this way, but the circulation in the opposite direction, okay? Provided that this is the normal, okay? Doesn't look like it, so the magnetic field is probably this way and the circulation is that way. But I'm summing through all of these things in here. At the end of the day, it's going to be mu naught times this current. And this current, is it positive or negative? It's going into the screen. Because this dot product is clearly involves, because this is a dot product, by the way. The dot product involves the cosine of the angle between them, and that's clearly from this picture, it's a negative value, it's a negative angle. Cosine of 180 degrees is -1. So this will be negative times the current enclosed, and the current enclosed is 4 amps. And mu naught, that's something that I should have written as something that is given, that is known also. Mu naught is 4 pi times 10 to the -7 in SI units. If you think of this one as being in Tesla, and this is in meter, and this is in amps, so it's actually Tesla meter per amp. That is the unit for mu naught, okay? So I need to plug in that value in here, so it's going to be negative 4 times 4, that's 16, times pi, times 10 to the -7, Tesla meter, because the amp and the amp, this is an amp and there is an amp in the denominator in here, will cancel, and it's going to be Tesla meter. As a matter of fact, from here, it's Tesla meter. Tesla times distance. So 16 times pi, if I have the calculator in here quickly, 16 pi's is 50.2654824574367. Obviously, that's not correct, because all I need is 2 sig figs. And the calculator is trying to tell me that it's far more precise than the actual thing. So it's actually just -50 times 10 to the power 7, or -5.0, if you like, 10 to the -6 Tesla meter, okay? Or -5.0 micro Tesla meter, okay? And typically, in the units for the magnetic field, it's of this order of magnitude. It's just so tiny, and that's because of the mu naught. Also, so that is part of the discussion. We solved, we answered the question, and we plugged in the units for all of these 2-3 steps in the same time. We justified the answers, and now we're doing a discussion. So this is actually a typical number of the answers in here. So we're fine with the correct answer in here. Let's do quickly path C now. Path C, I have 2 currents enclosed. I have I1 and I2. So this should be of Bdl. This is a line integral, so we're not really supposed to worry about it. So all of the currents enclosed. So it's a mu naught times -4 amps plus I2, and I2 is 6 amps. -4 plus 6, that's 2, times mu naught, and mu naught is 4 pi, 10 to the -8, 10 to the -8, I'm sorry, 10 to the -7, The answer is going to be Tesla meter, because again, the amp and the amp cancel. 2 times 4, that's 8. That's why I was thinking 8 in here. And 8 is about half this number. So the answer should be about half the other answer, except it's a positive value. Positive 2.5 microtesla meter. Okay? I'm just taking advantage of the result that was done before. Finally, on path D, the circulation on path D of BDL is going to be mu naught, again, sum of all of the enclosed currents. And path D actually encloses all of the currents that I mentioned before, I1, I2, and I3, albeit I1 is still negative in here on this path because we're doing the circulation in counterclockwise, whereas this contribution should be in the clockwise direction. So it's going to be in the negative direction. So again, it's mu naught times I1, which is -4, plus 6, and plus the last value is a 2 amp current. So plus 2. So -4 plus 8 is +4. And the answer is going to be 16, actually, pi times 10 to the -7, again, Tesla meter. And 16 is the same answer as before, except it's a positive sign, that's all. So it's going to be a positive 5.0 microtesla meter. Okay. Does this problem make sense to you guys?
Yeah, it makes sense.
Good. So the next problem in the list of the problems I mentioned is problem 61. And as I mentioned before, this problem was given actually as an exam, or at least something changed about it a little. And there was actually additional questions about it that's not included in here. It has to do with the linear tension on the strings in here. And that is the, so again, we're going to do problem 61. So the first step in here is to read the problem and pull the data that we have, the information that we have from it. It's a good idea always to draw the actual shape that was given to you. So what I have in here, I have 2 big wires. So let me pull a thick pen in here, the thickest I can have. No, it's too thick, probably this one's. So this is wire 1, and Control-C, Control-V, and copy it and put it in here next to its sister. And we're going to go back into the shape, to the wires, come back to this tiny wire and draw the actual suspending. Come on. Okay. Wow. Can I copy this thing from you? Because I like them so much. Control-C, Control-V. Wow. Okay. And this is where they're suspended from, okay? So this is how it looks like. So what we have in here, this separation between the two. Let me draw it in a different color so that we have at least. So this angle is actually 6 degrees. So this angle is 6 degrees, and this angle is 6 degrees. So I draw 2 of them. This is 6 degrees, and this one actually is 6 degrees, for a total of 12 degrees. And they tell me I need this distance actually between the 2 wires, okay? This distance, the whole distance, I'm going to call it D. So this is half D. So this is just D over 2 by symmetry, okay? Because this is 4 centimeters is given, and this is 4 centimeters. It's clearly D can be found from this right angle triangle, because this is the vertical. And in this right angle triangle, D over 2 is the opposite to 6 degrees. So d over 2 over the hypotenuse, which is 4 centimeters, is equal to sine of 6 degrees. That is basically something that I can tell from geometry. Again, there are things that were given to me that I need to be careful with. The currents, they say specifically in this problem, is flowing in the same direction. And it has to be, I'm sorry, in opposite directions. What am I saying? In opposite directions for the repulsion to happen. So what they're saying in here is that you have two wires and you run currents in opposite directions, so they repel one another. This is what we saw from this chapter, actually. Or did we do this problem? Oh man, wait a minute, I'm confused now. I'm sorry about this. We need to do this part. We didn't do it in the lecture for this class. That's part of the things that happen when you do 2 different sections on 2 consecutive days. No, we didn't do this part. So let's finish chapter 28. Sorry about that. Finish chapter 28. Otherwise, we cannot do this problem. And so it's very important that we add this one to the lecture, actually. So here is what problem 20, what this this problem is, okay? I thought we did this, and I know we did it for the other class. So what I have in here, I have 2 wires, okay? And these 2 wires have currents that I'm going to assume at this point in here that they're running in the same direction. They could be running in opposite direction, and that's fine. And that's exactly what the problem is saying. But that's fine. We're going to find the solution to that one very quickly. So I have a current I1 and I have a current I2, both of them running in the same direction. So my challenge is to find the force exerted by this wire that has a current I1 in it on wire that has a current I2 in it. So that's really the challenge. Since this is a wire that has a current, it's going to create a magnetic field in this region of space, okay, where this wire is. And how am I going to find that? We already did that. We already did that part of the lecture, actually. A wire can create a magnetic field around it. So this was the loop. We did the loop, but we also did the wire too. Here is the wire. So a wire at a distance y from it will create a magnetic field, and that magnetic field is given by, after we did the secant and integrated and everything else, mu naught I divided by 2 pi times the distance. So this wire in here that has a current I1 in it will create a magnetic field in this point, which is B1 coming from this current. It's mu naught I1 divided by 2 pi times this distance. And the distance between the 2 wires I'm going to call simply D, divided by 2 pi D. So there is a magnetic field where that wire is, due to the first wire, okay? Also from previous chapter, chapter 27, we saw that a wire that has a current running through it, which is I2 inside a magnetic field, which is B1, will be subject to a force. So I'm going to take a length L now of this wire, a finite length L of this wire. So there will be will be subject to this force. F on 2 due to 1 will be simply equal to I2 times L times B1. The direction for this force is as follows. I need to find, first of all, the direction of the magnetic field, B1. Because the current is going up, okay? That means the magnetic field is curling from one side, from this side, inward. And from this side, outward. Due to I1, it's going this way. So specifically in this point in space, the magnetic field is actually coming out of the screen. This value, the one that I calculated, it's coming out of the screen everywhere in here. For this segment of the wire. And it's the same quantity because all it depends on is just how far I am from there. So we have a wire that is subject to a magnetic field due to wire 1 that we can calculate. We calculated it actually before in chapter 28. And it has a current running through it, which is this way. Now I want to find the direction of this force. This force really is a vector force that is equal to I2 times L. L is in the same direction as the current, so it's pointing upward, crossed with B1, which is coming out of the screen. Now, L is going up. I mean, the current is going up. P is coming out of the screen, like this, coming to me. So the force now is going back into this wire. So when currents go in the same direction, the force is actually attractive. If the current was going in the opposite direction, if this current, like the problem that we have right now, if the current was actually going down, this L needs to be pointing down. So now, if I do a calculation again, so the magnetic field, the L is going down first. The magnetic field is coming out of the screen, so the force will be pointing in the opposite direction. So currents in the same direction, attract, which is kind of opposite to what we've been seeing in the case of charges. Charges of the same sign, whether both of them positive or both of them negative, will repel. In this case, currents, whether they are both going up or both coming down, they will attract, actually. So this is opposite to what we have learned in the past for the case of charges. And currents in opposite directions, or opposite currents, attract. Opposite currents, repel. It's opposite to what we have seen in the case of electricity. So opposite charges, they attract. Opposite currents actually repel. Same charges, positive, both of them positive or both of them negative, repel. The currents in the same direction, whether both of them up or both of them coming down, actually attract. So this is counter what we have seen before. So that's why the setup for this problem actually was in such a way that the currents are actually opposite to one another, so they repel one another, okay? Because they're moving in the opposite directions. So that is in terms of that value. Now, in terms of the magnitude of this force is simply equal to F on 2(1) is equal to I2 times L times B1. And B1 is mu naught I1 divided by 2 pi times the distance between them. Then, in this case, is equal to L times mu naught times I1 times I2 divided by 2 pi times the distance between them. So now we have that expression typically in this problem. So you will need this expression for this problem, okay? But typically we express this force per unit length. So F21 is the same by definition if F21 on divided by L. So now, because we're not given L, how long the wire that we're considering in here. So that's why we use the force, which has the units of a Newton per meter. How many newtons per meter are needed for this wire? And that is this force in here by definition. So it's going to be mu naught I1, I2 divided by 2 pi times d. Now, if you're asking what happened to wire 1, is it going to be subject to the force due to wire 2? Absolutely. There are two reasons for it. First of all, you can do the calculation. You can actually calculate. Again, the magnetic field in this region due to wire 2 is going to be inward, and it's going to be B2. And B2, similar to the previous expression, is going to be mu naught I2 divided by 2 pi d. That's this force. And now the current is going up. The magnetic field is going to be inward. So the force is actually going to be in this direction, opposite to the other one. So this is the force on 1 due to 2. It's going to be attracted toward the other wire. That's what I was saying earlier. And its magnitude, F on 1 and 2, is going to be mu naught times the same length. I'm sorry, mu naught. Sorry, it's I1 actually, times L times B2. And if you examine this expression and you sub the value in here, it's going to be identical to this expression. So F21 is equal to F12. The second reason why they should be equal and opposite is Newton's third law of motion. I have two objects in here interacting with one another, and one of them exerts a force on the other one exerts a force that is equal in magnitude in opposite direction. So F12 will be actually equal in magnitude to this number. It's going to be L mu naught I1 I2 divided by 2 pi d in magnitude. The direction obviously is going to be opposite. If this one is attracted in here, the other one is attracted to it in the opposite direction. End of the story. If the two currents are moving in opposite direction, this one is repelled, the other one also is repelled by the same amount. Okay, so that is the third law of Newton. So this is part of the lecture that we really needed to complete for us to do this problem in here. Make sense to you guys?
A little. I'm just kind of like processing it, but I think when we're doing the problem, it'll just kind of click in. I get the main idea of currents kind of going toward each other with like kind of the opposition with what you were talking about. Where instead of, repelling each other when they have these same kind of positive, negative kind of things, they attract instead. And of course, the forces interaction.
Okay, this is absolutely no exception to what we do in lecture. Most of the stuff we do the lecture, honestly, it stands kind of hanging in the air, unless we do problems with. Once they do problems, they start landing on where they need to be. Then you should be able to understand them better. Okay?
Yeah.
So that's the point I was making in the beginning. So we have a problem now. We have two currents moving in opposite direction. Both of them have the same magnitude of currents. If you look at the problem. So now we know it's going to be a repulsion because two currents moving in opposite direction, they will actually repel one another. Okay, so opposite to what we intuitively think of in terms of charges. So that's all the information that was given to us. They give us 6 degrees, they give us the length of that wire, and they want to know the current I. So that's a question that we were supposed to find, the current I. I need that distance because if I want to find this force that I just calculated in here, so the force, first of all, on either of the wires, I'm going to just call it F, is equal to mu naught times the product of the two currents, and they are the same. So it's going to be I squared divided by 2 pi times this distance, which I need, and it's going to be coming from geometry. It's coming from this triangle, actually, that's all. Because if I call this whole distance d, then this is d over 2. And the d over 2 from this right angle triangle is just the hypotenuse, which is 4 centimeters. That's the length of the suspending wire, times the sine of the angle, which was given to us 6 degrees. From here, we can find that this d is simply equals to, what is it? 2 times 4, that's 8. 8 centimeters times sine of 6 degrees. So that is basically the d that I need to plug in into this distance. So this is how far apart they are, okay? This is how far apart these two wires are. Okay, so we need that. We don't know what F is, so we really need times L times some length in here, which is not given, which not even there. So we need to multiply it by L. If I look at the expression, it's mu naught. It's mu naught times the two current divided by 2 pi the distance times L. So that L is not given, so we don't know what it is. Please do not confuse it with this L that was given. This length is for the wire in here, the suspending wire. It's not the length of the actual wire carrying currents, okay? So that's not given. So this L better not be part of the answer, or we have to find it or something, okay? One of the two. So this is so far we analyze all of the problem. Now let me take a wire, any wire of this two, and look at it from a statics perspective. So the wire, I'm going to take a segment of length L again of this wire. So this segment of length L of this wire, they tell us also something else that I didn't, they tell us the linear mass per unit length for this cable is 0.0125 kilogram per meter. Okay, so if I take an L length, the mass of that element is mu times L. Okay, so this is how much mass per unit length, but I took a finite length L. This one is suspended at this angle. This is the vertical. This is the tension that suspends it. This is mg pointing down. And this is the tension T. I'm sorry, the force F, the force of repulsion that repelled it from the other wire. So this is the magnetostatic force that is basically pushing them. So I'm going to come in here and look at it from this angle and see exactly what's going on. M is this mass. So from that perspective, this wire looks like this. Tension T. This is the three body diagram, by the way. mg and the force F. What I'm going to say in here, this is a static equilibrium, so the sum of the forces are equal to 0. I'm going to take this one to being the x-axis and this one to being the y-axis. This angle is given to be 6 degrees, not 60, 6 degrees. Okay? So that is basically what was given in this problem, and we have everything. So we're going to write the equation in here in the x-axis, like what we do normally in physics 4a. The component of the force F is a negative F. The component of the tension T is going to be equal to this component. And that is the opposite to 6 degrees. So that means we're dealing with the sine of 6 degrees. So it's a positive, because it's on the positive x-axis, T sine of 6 degrees, plus the component of mg along this x-axis is 0, because there is no component in there. So that's equation number 1. I'm going to do the same thing for the y-axis. And I'm going to look to the force F. The force F has no component along that direction, along the vertical direction. The component of T is positive, actually, and it's actually this component. And this is clearly the adjacent to the angle 6 degrees. So it's actually a positive value also, T times a cosine of 6 degrees. And the component of mg is negative mg, is equal to 0. So we have everything that we need for our problem to solve for this F, because we need to have F, except that we have that annoying L in it. Okay, let's see if that L will cancel out. Okay, so let's find F from this equation, the first equation. So F from the first equation looks like equals to T times sine of 6 degrees. But I don't know what T is, so I need to go back into the second equation and find what T is. So the second equation tells me that T is equal to actually mg over cosine of 6 degrees. Okay, so if I plug this in here, then this will become equal to mg times sine of 6 degrees divided by cosine of 6 degrees. And that is actually the tangent of 6 degrees. So we have F. And we have F from the expression that we just saw, which is mu naught I squared times L over 2 pi d. So we have it from the previous equation, mu naught times F squared times I squared, not F squared, times I squared times L divided by 2 pi d. Okay. If you're worried about d, we already found what d is from the geometry of the problem. Here is d. It's 8 centimeters times sine of 6 degrees. But I have to be careful in here for this number to use it actually in meters. Okay. So if we're careful enough in here, m also we need it. M is actually equal to mu times L. That's where the L is going to cancel. So let's sub everything. So we have mu naught I squared times L divided by 2 pi times d equals to mu times L, and that is where the L is canceled, times g times tangent of 6 degrees. Okay. And once we sub for everything in here, we should be in business. So that means I, because we need I actually, that's the whole exercise of this one, is to find I, is the square root of this mu, which is the linear mass, times g, times tangent of 6 degrees, times d, I mean 2 pi, so I'll probably have to write 2 pi in here, times d, and d is 8 times 10 to the negative 2 times a sine of 6 degrees. Sine, oh man, 6 degrees. So we took care of everything in the numerator. Now we have to deal with the denominator. Denominator has mu naught in it, which is a constant, 4 pi times 10 to the negative 7. And that's it. Okay, that's it. That's all the things that we need. Obviously, if I sub in the value in here, I have 4 pi and I have 4 pi, and I have a sine times tangent, which is sine squared divided by cosine theta. So everything in here is going to be equal to the square root of 0.01225 times 9.8 times sine squared of 6 degrees. If you're worried about where the other sine is, it's in here, okay? Times 2 pi times 8 times 10 to the negative 2 divided by mu naught, which is 4 pi, times 10 to the negative 7 times the other part of the tangent, which was a cosine of 6 degrees. Okay? And if everything is correct, I should be a value in here. Let's see here how much it is. So let me stop sharing the screen in here. And let me share with you, share the calculator. Because when I did it with the other class, we ran into a problem. We get an indeterminate expression, and we couldn't figure out how where that indetermination was coming from. And now I think I have a feeling that I know where that indeterminate. We were able to calculate it, even with their own calculators, they're into the same problem, okay? So square root of 0.0125 times 9.8 times sine squared. So I have to open parentheses sine and then square 6 degrees. This calculator is already in degrees, okay? So I don't have to convert anything to squared, okay? Times 2 pi. Okay, the pi and the pi cancel from the numerator and the denominator. As a matter of fact, I have 2 pi and I have a 4 pi, so I'm going to just write to 2 in the denominator so that I don't have to get any unnecessary step. As a matter of fact, 10 to the negative 2 and 10 to the negative 7 is going to be negative 5 in the denominator, so that I don't have to also carry that many things in here. So it's going to be just times 8 at the end in here, divided by, open parentheses. So again, I'm left with 2 times cosine of 6 degrees times 10 to the negative 5, because I already took care of those powers in there. Close this parenthesis and now close the square root parentheses, and everything should be correct. Okay, so I think the problem that we ran into the day before was with this is the correct answer, by the way, 23.2 amps, okay? So we use the tangents, and the tangents around 6 degrees, the calculator might, it's within the margin of error so that it can be negative. So the square root of a negative number doesn't exist. So, but if you do it as sine squared, you're going to be in good shape. So anyway, so let me stop sharing that screen and let me go back into the calculations again. Share. Okay. So the answer is 23.2. How many sig figs did we say in this problem we had? Oh, we didn't. We really have to think. We have 4 sig figs according to the angle and everything else that was given to us. Three sig figs, I'm sorry. So we have 3 sig figs, so it's 23.2 amps. And that is a big current, by the way. This is a huge current. So that's part of the discussion. Again, we're toward the end. So the current that we have found is a big current, and there is a reason for it, because of that 10 to the negative 7 in front of everything, in front of the magnetic field. So even though you have a magnetic field that is splitting the two, but you're multiplying everything by mu naught. And mu naught is the order of 10 to the -7. So you really need to have a huge current in here, even though 23, when you square it, is going to be about what, 400 and something. You need that to compensate for this one. And the distance you're going to achieve is a very tiny distance. I mean, this is the distance, which I didn't calculate, but it's an 8 centimeters times sine of 8 times the sine of 6 degrees. And this number, 8, is 0.8 centimeters, or 8.36 millimeters. So it's a very small separation. So if you think of a millimeter as the width of a hair, this is about 8 pieces of hair lined up one next to one another. Okay, so that's how far apart these two wires are, because 6 degrees is a very small angle. That's why we're getting this much separation, which is not a lot. So this distance is small, which makes this force big, plus the current needed to be big to compensate for that mu naught. So that is part of the checking your answer and discussing the result and everything. So the entire steps that were done in here, all of them. So I'm hoping that this is actually learning on how to solve problems, because it's critical whether you're doing it in an exam, whether you're doing it in a homework, or whether you're working later on in the field and trying to solve problems. So this is still the same process. Okay. So if you guys don't have any questions, we're going to jump into problem 62. I'm going to do problem 62 quickly because I really want to do, and we still have about half an hour. I want to really do problem 67 thoroughly too, because it's a very important problem. 67 and, as I was saying, 63 are similar, okay? Except 63 has to do with the integration of an exponential. The other one has to do with the integration of polynomials, okay? And then we probably have to discuss problem 49. Okay, so we have quite a few things to talk about. So that's problem 62. So problem 62, basically they gave you this shape. And they want to find the magnetic field in the center of the shape. So you have a current that is going in this way. So it's going to go clockwise along the entire, basically, shape, okay? Doesn't matter where you start, you're going around the clock, coming back to where your starting point is. However, from the vantage point of this one in here, for this point P, this element, so we are looking at 4 different contributions. The DL in here and the R hat in here, they're in the same direction. So when I do this product DL crossed with R hat, this will involve a sine of 0 degrees because these 2 vectors are parallel. So the contribution to the magnetic field from this point is 0. This point in here, the DL actually is in this direction. The R hat is in the opposite direction. It's toward the point P, which is right in there. So in this case, it's going to be involving a sine of 180 degrees, which is going to be a 0, albeit with a negative sign, okay? Because sine of anything above 90 degrees is going to be, it's a 0. What am I talking about, okay? It's 0. Now, in this case, the contribution from this segment. Now, the current is going clockwise. So the contribution is going to be coming out of the screen. So this contribution here is going to be out of the screen because the current is going counterclockwise. So the current is going counterclockwise. And so this contribution is going to be coming out of the screen. This distance is A. They gave you that. This distance is B. They gave you that. But this one is actually going into the screen. So I have to take into account the other contribution, which is a negative contribution, because again, as the current is curling in the clockwise direction, the magnetic field is going to go into the screen. And I'm going to use this result from the previous chapter, from this chapter, I'm sorry. And this result is this value in here. Where is it? For the loop, basically. This one, except that I have half a dome. I mean, I have a dome. I don't have a full loop. So it's going to be half this value, whatever this value is. So this is the value that we ended up with for inside the circle. And this is where inside the center of the loop. except we don't have a full loop, we have half a loop. So the contribution is going to be just half. So it's going to be mu naught. And then I have to use the specific radius. In this case, the first radius is A, the second radius is B. So the first one is going to be, so the total magnetic field in that point is going to be zero. First of all, the contribution from this one, which is 0, plus the contribution from the semicircle of radius A, plus 0, minus, because the other one is going into the screen, minus the contribution coming from the upper dome in here, because it's circulating clockwise. So in this case, this value is mu naught I, and it's the same current flowing through all of them, I. Okay, so it's mu naught I divided by 2 pi times, sorry, there is no 2 pi, it's 2 divided by 2 and 2, half of that, so it's going to be 4 times A, plus 0, minus, again, mu naught I divided by 4 times the distance, which is B now. So that's all there is to it. Now the magnetic field is going to be, B is going to be mu naught I over 4 times 1 over A minus 1 over B. And the common denominator in here is AB. And the numerator is B times 1 minus A times 1. So I can express this expression in here in terms of both of them as being mu naught I times B minus A divided by 4 times AB. So this is the magnetic field due to this one. And which way it's coming? It's going to be coming out of the screen. The reason why is because this value, 1 over A, is bigger than 1 over B, because A is less than B. Written in this format, it's clearly positive. B minus A is positive because B is greater than A, and A times B is just the radii, which is positive. It can never be negative. So in this case, the magnetic field is coming out of the screen. So that answers problem 62. Okay, so let me jump into problem 67. So problem 67 involves a little bit more work in here. So it says a long, straight, solid cylinder oriented with its axis in the z direction carries a current whose current density is J. The current density is symmetric about the axis, the cylinder's axis. Is not constant, but varies as to the relationship. So we have a wire that carries a current, and this is the wire, okay? As a matter of fact, this is the z direction. If I take this wire and make a big cut cross in it, so this is how the wire looks like, okay? So for me, if I cut it, that cross section looks like it's part of a disk, actually. So the wire is coming out of the screen. The current density in here is given by this expression. J as a vector. So this whole radius of this whole thing is A. So this is the center. This whole radius is A. So it's given by, actually equal to 2I naught divided by pi A squared times 1 minus R over A squared in the K hat direction, in the same direction as I'm talking about. So this is the K hat direction. It's coming out of the screen. So that is where the K hat is pointing. For R less than or equal to A, and it's equal to 0 for R greater than or equal to A. For anywhere in here, there is no current. So there is a current density. For R equals to 0, it's clearly equal to 2I naught times pi A squared. And then it starts to decrease when R is equal to A, 1 minus A over A, which is 1, 1 minus 1 squared, which is 1, 1 minus 1, which is 0, 0 times whatever you have in there, so the current vanishes at the boundaries of this cylinder. So this is a cylinder going into the screen, okay, and out of the screen, and this is a cut from it. obtain an expression, so part A, show that I naught is the total current passing through the wire in this cross section. So how am I going to do that? I'm going to take a cut in this sphere around this center, of course. So I have to take it into a distance r from it, and r plus dr. So this segment only, this strip, if you wish, is of width dr. Okay. So this is, if I open it, if I take scissors and cut actually the strip, this is how it looks like. It looks like this. The length of it is going to be the circumference of this circle whose radius is r. And that is 2 pi r. So this distance is 2 pi r. And this distance is actually dr. So what is the area of this strip? What is dA now? Basically, I have a rectangle whose width is 2 pi r and its height is dr. What is this area?
Area would just be multiplying 2 pi r and dr, so yeah.
Correct. So that is the area dA of this strip. And how much current do I have in there? In this strip, I have J times the area. And the area, by the way, is in the k-hat direction too. The area is a vector too. So the area is in the k-hat direction, and the vector is in the k-hat direction. So JDA is simply equal to J times dA, and that is equal to whatever that value. So this is the current dI in this strip, in the strip. Okay, this one. Okay, so again, I'm going to sub the value of dA, which is 2 pi r dr. The thing with this one, r now, if it changes from 0 to big A, then I have swept the entire disk. Okay, then I have found the entire current, because this is just a dI in here, and I need the entire current. So because this is a current density, this is a current per unit area, basically. J is a current density, which means per unit area. And this we saw it way back in chapter 25. Okay. So if I multiply by the area, now I have a current, except I have a current only on the strip. I don't have the entire current, and they want me to find the entire current and show that it's actually I naught. So I will be the sum from 0 to r of all of this quantity, which is J times 2 pi r dr. And now J, I have that expression for J, which is given in here, 2 I naught divided by pi I squared times 1 minus r squared over a squared. And the k hat, of course, is already consumed in the dot product. So this is going to be 2 times I naught divided by pi a squared times 2 pi, the integral from 0 to r. I am left with an r dr times 1 minus r squared over a squared, and that's it. Now I can do this calculation in here. First of all, I need to get rid of this 2, this pi, and the 2 times 2 is 4. So the expression now I have for the current, I'm sorry, the integration from not from 0 to r, it's from 0 to a for the entire sphere, okay? So the integration from 0 to a, from not the entire sphere, the entire area, I'm sorry. So it's from 0 to a. Before I do that, let me write the actual numbers in here. I have 4I squared, well, they are constants. 4I naught, I'm sorry, divided by a squared, the integral from 0 to a of, first of all, r times 1 is r, minus r cubed over a squared, and that is dr. So the first part of the integration is just the integral of r dr, or the integral of x dx, is just x squared over 2. And the second one is x cubed dx, or r cubed dr, and that is 2 also. It's going to be x to the power 4 over 4. So if I sub the values, this will be equal to 4I naught over a squared times. This is going to be r squared over 2, evaluated between 0 and a, minus r to the power 4 over 4a squared, evaluated between 0 and a. And this one, the upper limit is going to be a squared over 2. And this, the lower limit is going to be 0. The upper limit in here is going to be a to the power 4 over 4a squared. And I already have a cancellation in here. And the lower limit is going to be 0. So I will have a squared over 2 minus a squared over 4. And this is a squared over 4. And the 4 cancels the 4 in here. And the a squared cancels the a squared in there. So this expression then becomes equal to the total current is simply I naught, exactly what we were supposed to show, okay? Exactly what we're supposed to show for this question, okay? Please do these calculations. Please make yourself at ease with this kind of calculations. Make sure you're accustomed to it and ready to do it, and you know exactly how the steps are. If you have any doubts about it, please let me know. While I was doing this solution, while I was going through solutions in here, which is not always algebraic, by the way, like this one is actually an integration, I was justifying everything, including how the area came about and the steps into the boundaries of integrations and carrying actually the integral. And where I got this expression, I got this expression actually by the definition of the current density. The di is equal to dA. So that's how we defined it in chapter 25. And then we use that. So this is a physical law. Now, this has nothing to do with physics. This is actually geometry. I mean, the integration. And then carrying down the integration. Where did I get this stuff from? It's from the rules of integration. Again, I'm trying to justify the steps as I was going along and did the calculation. At the end, I found the answer exactly how they want me to show it. And in here, in discussing it, exactly what we were supposed to show. So this is correct. So this is part A. Part B, using Ampere's law, derive an expression for the magnetic field in a region greater than A. So what would be the magnetic field in this point? B in here. First of all, the magnetic field is coming out of the screen. So the magnetic field will be actually this pointing upward in here. It's going to be a vector in this point pointing up. Okay. Again, all you have to do is just the current is coming out of the screen, so it's going to curl around it in this way. But the value of it is going to be given by, so we're going to use a Gaussian surface in here, and the Gaussian surface has to be like this, which is just another circle whose radius is r. Okay, that's it, where r is more than a. Okay, so if we do that, then part B now. So we chose, not a Gaussian, we chose an Amperian loop, and the loop is actually a circle whose radius is r. And the circulation then, dl, is parallel to B, and B is constant. B should only depend on r, because if this thing only depends on the charge in here, so I mean it depends on the current. Since the current has this radial symmetry, so if I rotate the wire one way or the other, the magnetic field should not change. So it's the same value everywhere in the same direction, as long as I am still on the Amperian loop. So because of that, then I'm going to use Ampere's law, actually. And Ampere's law tells me the circulation about this Amperian loop, which is a fictitious loop, it doesn't exist, okay, is going to be equal to mu naught times the current enclosed, and the current enclosed is I naught. I just calculated it. The entire current enclosed from 0 to A is just I naught. So look, when you're given problems like this one, and you're asked to solve them, sometimes take advantage. Okay, let's say, for example, you couldn't prove that I is equal to I naught. You can always answer part B. because part B, you can assume that I is equal to I naught. So the circulation of the magnetic field around the imperial loop is going to be that one. And B is parallel to DL, so the dot product becomes just BDL. Furthermore, B is constant around the circle. So this is going to be a circle now of radius R. Okay? So the circumference for that is 2 pi R. That is the circumference, because we're going to circulate around the path. So the B will come out of the integral because it's constant, depends only on R. And since R is not changing, we're on the circle. So it's going to come out of the integral. And basically the circulation of dl now is just dl, I mean, across the entire, so the integration becomes just simply the integration from whatever value to 2 pi R, okay? And this is equal to mu naught I naught. So the whole thing is mu naught I naught divided by 2 pi R. Again, without doing any kind of vector analysis or anything like that. The only thing is we use the symmetry of the problem. The fact that we have cylindrical symmetry and the current density doesn't depend on the angle, it depends only on R. So if I rotate this cylinder one way or the other, the magnetic field should retain its direction because it depends only on J, and J did not change as far as we're concerned. If I tell you to close your eyes while I rotate that, you wouldn't notice that something has happened because J depends on the direction K hat. And since we didn't do anything with K hat, we did it only in the XY plane. So in this case, it should not matter, okay? The distance is the same. So the direction of B stays the same. And it's parallel to the direction where we're circulating on that circle. Since R did not change, B stays the same because of the integral, and then at the end it's just B times circumference of the circle. So we didn't actually do the integral. All we did was note that the circumference of the circle is 2 pi R, and then use that to our advantage, use symmetry and things like that. So the imperial law is similar to Gauss's law. It takes advantage of the symmetry of the problem. And the steps for using Ampere's law is similar to the steps using Gauss's law. In a sense, you have to identify the symmetry and choose the proper shape. In the case of Gauss's law, you use a Gaussian surface. In the case of Ampere's law, you use an Amperian loop. And then the second one in here is you may introduce additional parameters to your shape. If it is a Gaussian surface, you might add some parameters to the surface. If it is an Amperian loop, you might add some parameters to the Amperian loop. The answer should not depend on what you add, because the entire surface in the Gauss's law or the entire loop in Ampere's law are fictitious. They're not real. They're just some convenient way of solving the problem. Once you do that, when you go through the calculation and you find the electric field in the first case, or find the magnetic field in the second case, you're done. Okay, that's it. That is the magnitude, and you argue it by symmetry of the direction. So that is the similarities between the two laws. Okay, so we were able to find the magnetic field outside as long as R is greater than or equal to A. We need to do the same stuff in here. Unfortunately, we're running out of time. So I'm going to do it quickly and hope that you guys, what I'm going to do also, because there were some more discussions in the other class, so I'm going to include their video also, and probably or something in there so that you can watch it, or maybe down the road we're going to work out those labs, lab sessions, to do more problems in them. Anyway, so the second one in here is actually to go back into the same shape in here and carry the calculation not from actually 0 to can I make it even bigger? Just to R, okay? So we're going to take a dummy variable now, R prime, and vary R prime. So this is the R prime and everything, and vary R prime from 0 to just R, because we want to be inside the surface now. So the calculation will be identical to what I did in here, except the name of the variable has changed now from R to R prime, and J now will include an R prime instead of an R in it. And the boundaries of integration change from 0 to A to 0 to R. So everything will be similar up to this point. So part C now, we're going to find the current enclosed within the distance R from the center, from the central axis. Okay. So if we go a distance r, the boundaries of integration will be just the same stuff in here, except the boundaries of integration will be from 0 to r, from 0 to r. And everything else should be the same. So I sub r now, which depends on how far we are from the central axis, is going to be mu naught for I naught squared over a squared. That should not change. Times open parentheses. The boundaries of integration, as I said, so the dummy variable now is r prime, actually, not r. So it's going to be r prime squared over 2 integrated between 0 and r minus r prime to the power 4 over 4. No, was there a 4 in here to begin with, or just a 2? No, that's a 4, I'm sorry. Over 4 times a squared, and again, the boundary of integration from 0 to r. If we do that, and I didn't make any mistake, then this should be r squared over 2, because the lower limit is 0, and this should be r to the power 4 over 4a squared, and the lower limit is also 0. So the value in here should involve for I naught over a squared times r squared over 2 minus r squared, or r to the power 4, I'm sorry, over 4 a squared. Obviously, we can take r squared as a common denominator from here, and we actually are going to take the 2 from the denominator. So it's going to be 2I naught r squared over a squared times 1 minus r squared over 2a squared. Okay, so everything albeit the same. So this is the expression for I sub r. If I apply Ampere's law, it's going to be exactly the same thing now, except that the Amperian loop now will be exactly this one. And it's going to enclose this much current. So the current enclosed is the one that I just calculated in here within this region. And that is times mu naught, of course. Did I include a mu naught in here? In this calculation? For the, yeah, it's included, so we're good, okay? So now, in the last part in here, so what we're saying in here is that the circulation, again, of Bdl must be equal to mu naught times I sub r, times this value that we found, okay? And this one, again, by symmetry, is going to be just pi times 2 pi r, and this is equal to mu naught times this number in here, which is 2I naught r squared over a squared times 1 minus r squared over 2a squared. Obviously, I have some cancellations in order, an r cancel. I mean, one of the r squared cancel. And the 2 and the 2 actually cancels also. And the magnetic field inside the region now will be dependent on r. So B, I mean, it was dependent on r also in the previous version, but it was actually simply dependent on r. Now it's going to be mu naught times I naught divided by pi times a squared times r, because I'm left with an r in here, times 1 minus r squared over 2a squared. Note that b sub 0 is equal to 0, okay? And b sub a is not necessarily equal to 0, it's actually equal to mu naught I naught. A squared and a cancel, so I'm left with the pi times a, and I'm left with 1 minus 1 over, a squared over a squared, that's 1/2. So it's going to be equal to 1 minus 1/2, that's in 1/2. So it's mu naught I naught divided by 2 pi a. This value of b sub a should match the value of b sub a that we computed in here, because this one also depends on r. So b sub a from here is equal to mu naught I naught divided by 2 pi times a. So the function magnetic field in here is continuous at the point A, right at the boundaries of the region where there is a wire and where there is no wire, where there is current and where there is no current. The same magnetic field, but the derivatives should not be the same. Okay, the derivative may be different, so that is something that we can explore down the road. The point being, in here we found the magnetic field inside and outside of this region using what we know about this one. Okay. I think the session is over. However, let me say a word or two about these two problems. Problem 60, No, problem 63 is identical to this problem, with the exception that this current density changes. So instead of doing this integration over this polynomial function, we're going to be doing it over an exponential. It has already 1 over r in it, and the area will bring another r in it. So the r and the r cancel, and we will be dealing purely with the integral of an exponential. So that problem is, in a sense, a little bit easier than this one, but I need you guys to carry it. If you have difficulty with it, please let me know, okay? Problem 49. Problem 49 has 2 charges. One of them going this way, and the other one is going this way. One of them actually has a positive charge, and the other one has a negative charge. And you're supposed to find the magnetic field and a point in here. For that, you're going to use the formula that we started with, that B for a point charge is equal to QV crossed with r hat divided by the distance in here, divided by r squared. Don't forget we have a mu naught divided by 4 pi in here, okay? So here is the deal. You have a positive charge in here, and you have a negative charge in here. You're given this distance, which is 0.3, I think. Yeah, 0.3 meters, 30 centimeters. You're given this distance, 0.4 meters. And you can find this distance using the Pythagorean theorem, because this is the origin. And so this is 0.5 meters, actually. And this charge is given to you, and it's a negative charge. The velocity is pointing this way. This is pointing this way. I'm talking about problem 49 now, okay? And so this velocity is given, this velocity is given, so this is V1 or V plus, and this is the V for the minus, so they're different velocities. And I want to find the magnetic field in here. For this one, V is pointing this way, and r hat is pointing this way, okay? This is V, this is r hat. V is actually in the r hat direction, and r hat is actually in the negative j hat direction. So if I form this cross product, forget about the values in here. The values of V is given. The value of r hat is 1. Okay, it's actually equal to negative j hat in magnitude. And Q is given. R is this 0.3 meters squared. So in here, I have to form this cross product. This cross product is negative of I hat times j hat, and I hat times j hat is k hat. So this magnetic field is going to be pointing into the screen from this charge. Okay, if this is I hat and this is j hat and k hat is coming out of the screen, so it's going to be pointing into the screen. Now for this charge, again, V minus is actually pointing in the j hat direction. You can clearly see from the geometry. And the r hat is actually pointing in this direction, which is a minus, so crossed with a minus I hat. Okay, so if I'm careful with this calculation, I'm going to put a minus j hat crossed with I hat, which is actually equal to minus positive I hat crossed with j hat. When you reverse the order of the cross product, the sign changes. And this is positive k hat. However, there is a negative charge in there. So the answer will be, because of the negative charge, you will be in the negative k hat direction too. So that 2 is in negative k hat direction. So the value would be just the sum of the 2. So here, you have 3 negatives to make it negative. You have the negative coming from the charge. You have the negative coming from the direction of r hat, and they have the negative coming from the cross product, okay? Because j hat crossed with I hat is actually negative k hat. Times the negative becomes positive, times another negative from the charge becomes negative again. This one is outright negative because it's only one negative. The charge is positive, the velocity is positive, but r hat is negative. So you only have one negative in here that made it a negative. So you have one negative in here, you have 3 negatives in here, and the direction of the B field is in the negative direction. That takes care of that problem. So we can find the magnetic field in the origin. Then they tell you the force exerted by one charge on the other from the magnetic point of view. So I need to find, for example, in either of those two, if I find one, I find the other using the third law of Newton. So again, I know this velocity is in the I hat direction. I need to find the r hat. This is where the r hat is. It has 2 components. One along the j hat direction. I'm sorry, the velocity is actually in the j hat direction. One is along the j hat direction, and j hat crossed with j hat is going to be 0 anyway. So the only one that matters is this one that is in the negative k hat, negative I hat direction. That is going to give me a value. So if I find this r hat, which is in this direction, so this is the component that is going to matter in here. So we find the b hat, due to the negative charge in here, Once we find the B, we're going to use Lorentz force on this positive charge. It's just going to be its charge, which is Q. So the magnetic field will depend on this Q, by the way, okay? And don't forget this Q is negative, so this B in here might be flipped on you again, okay? So it's going to be on this Q now, crossed with this V now, crossed with the magnetic field that you find in here, no matter what that magnetic field in here. So if you have difficulty with this problem, please let me know, communicate with me, let me know. I can send you the solution with an explanation. And if you still have issues with it, please let me know. I think we are about 9 minutes over time. Okay, so again, in the lab this afternoon, I'm going to send the instructions, basically the video instructions. And if you guys choose to ask questions, there is no problem. You already had the written instructions, so you will have the video instructions for it. It's a short lab. The reason why it's short is because of the fact that we had to cancel a big chunk of it, which is the motor, building the motor, because the materials never arrived to campus, so I don't have them for you. So the lab is actually a very, very shortened version of the lab. Okay. I'll see you guys most likely next week on Tuesday. And please send the questions. I rely on you doing this 2 problems. And if you have any questions or you have difficulty, please let me know, communicate with me, and I will be more than happy to provide the written solution for you guys. And if you still have questions, please still ask questions. Let's make sure that everything is hammered and clear and understood. I don't want anything to be vague or not understood. Okay? Sounds
Alrighty.
good?
Yep.
Very good.
Sounds all good.
Yeah, all good.
Well, let me stop the recording.